4.1, exponential functions, and section 4.2, graph of exponential functions. Exponential functions are used to model the growth of population. For example, here, I have taken this example from the textbook as an introduction. And it says that in India, the population is about was about 1.25 billion people in the year 2013, right? Anna, welcome. We just started with section 4.1, 4.2, talking about exponential functions. Okay, so the example from the textbook mentions that in India, the population was 1.25 billion people in 2013, and it's growing at a rate of 1.2% each year. Now, if this trend continues, it says that the population will reach China's population or even exceed it in the year 2031, right? Exponential growth always tells us that something grows very rapidly, very rapidly. So in order to understand this better, let's do it mathematically. Let's do it mathematically. Let's try to use an example here. For example, we're gonna compare linear growth with exponential growth. All you guys that just joined, welcome. Jay, Anna. We just started, okay, with the lecture. We're talking about exponential functions. Okay, so suppose we have linear growth. Look at this sequence of numbers. It starts with 1. Imagine this is like a population in a town, then 3, then 5, 7, 9, 11, 13. And then on the right, we have exponential growth. It started at 1, 2, 4, 8, 16, 32, 64, 128. Anyone could tell me, based on this sequence of numbers, what is happening to go from the previous term to get the next term? What are we doing to get here the next term, to go from 1 to 3, from 3 to 5, from 5 to 3? Anyone could write in the chat what is taken, what is gotten. If you are good at pattern recognition, you should be able to determine the rule sort of for this. What should be that? Anybody? Aha, I see someone wrote something on the chat. Yeah, Anna, very good, Anna. Adding 2, right? Yeah, no hard to see that if we add 2 to the previous, we get the next, right? Adding 2. Yeah, it's a simple rule. Adding 2 to the previous gets you the next. And this is what, growing by Gabriela also, right? Yeah, this is what basically determines linear growth. Now, if you graph the population versus time, then there is going to be a formula. Anybody could tell us the formula? It starts at 1, the population, right? But then what do we add anytime to get the next? If this is time and this is population, what's the formula to get the population from the time based on this? 1 plus what multiple of 2 or t? Yeah, I see. Someone figured it out. Yeah, it's not hard to figure this out. Gabriela, excellent, Gabriela, excellent. Yeah, made my day. Twice, right? Twice time, right? At time 0, this is 1. At time 1, 2 times 1, 2 plus 1, 3 times 3, you know, 2 times time 2, 2 times 2, 4 plus 1, 5, and so on, right? This is linear growth. Now, if you graph this linear growth, 0 goes with 1, right? Time 0, population 1. At time 1, 2 plus 1, 3. So we're talking about this point, right? It's here. At time 2, 2 times 2, 4 plus 1, 5. So This is 3, 4, 5. That's up here, right? And if you connect these dots, if you connect this dot, not too hard to see that they determine a straight line, right? A straight line, which tells us that the rate of change is just constant, right? Rate of change, constant. And we can even find this rate of change that is constant, right? It's 2 people per year, right? Per year, huh? The slope of this straight line, right? Now, on the right here, we have the exponential growth. We start with 1, population starts with 1, but then what is happening? Anybody could tell us what is happening to go from the previous to the next term? What arithmetic operation are we doing here? You can write it in the chat, or you can say it verbally, right? Gabriela, excellent. Doubling, right? Multiplying by 2, excellent, multiplying by 2, times 2, times 2, times 2, times 2. And this is basically one of the main differences between linear growth and exponential growth. For linear growth, you add some constant amount. For exponential growth, you multiply by some constant amount, in this case 2, right? For both. Now, if we graph population versus time, and we write our formula, what should be the formula? I will give you a hint. Start with 1, right? Here, we added to this one twice t, but what should we do here? Instead of adding, probably we should multiply, right? But multiply by what? By what is a power. It's a little bit tricky to figure it out. Some power of some number. What do you think one should be multiplied by every time you get to the next, to the next, to the next? Yeah, look at this guy, right? 2. I think 2 should be the base, right? So 2 raised to something. Yeah, it's yeah, okay. So the first time I multiply by 2, then 2 times 2, 2 to the second, 2 times 2 times 2, 2 to the third, 2 to the fourth, 2 to the fifth. In general, 2 raised to the t, right? To t. You follow, guys? 2 raised to t. Yeah, very good, very good. Excellent. Now, notice, right? Linear growth, exponential growth. Now, if we graph it, for 0, 2 to the 0, 1 times 1, 1. For 1, 2 to the first power is 2 times 2, 2, right? 2, so that's double, right? 2 here. For 2, for t equal 2, 2 to the second power, 4. 4 times 1, 4. So 1, 2, 3, 4, right? The next should be 4. And the next, for 3, it blows up. 2 to the third power is 8. 8 times 1, 8. So 1, 2, 3, 4, 5, 6, 7, 8. Up here, all the way up here, right? Up here, so blows up. So let me just do it in blue. So it's a curve, a very steep curve, right? Curve. So the curve grows very fast, right? Very rapidly, fast. And to the point that if you continue the calculations, you were gonna see really huge output values there, right? So it's the curve, very steep curve. It is the graph of p raised, p equal 1 is nothing when you multiply, right? So it's p equal 2 to the second power, right? Yeah, very good, guys. Same as p equal to t power. This is the way. Now, what here the rate of change was constant, the slope of the line, right? Straight line. Here, what is constant is the a percent of the growth. Okay, so rate of change, constant as a percent, And what percent? In this case, 100%, right? To get that to the next, the first grew 100% of itself, right? It gets double itself, right? 100%, constant rate of change is a percent. All right, guys. So now, when you think of exponential growth, think of something growing very quickly, rapidly, right? Rapidly, quickly. Yeah. So, very good. Now, so far, we have seen functions like this, right? F of x equal x squared, g of x equal x cubed, and so on, right? When we study polynomial functions, where the base is a variable and the exponent is some number, right? Some number. Now, however, it is possible to form functions like f of x equal 2 to the x, or even g of x equal 3 to the x, just like this function, right? Where the base is a number, right? Like 2, for example, or 3, and the exponent is a variable, right? It's a variable. Mathematicians study these functions. They call them exponential functions, right? Because they resemble exponents. And when graph, they show something that grows very fast. All right, these are called exponential functions. Formal definition here: the exponential function f with base b, there will be always a base, in this case 2, in this case 3. In its basic form is defined by f of x equal b raised to x. That's its basic form. Some number raised to some variable, in this case x. Now, the base must be greater than 0. Greater than 0. Cannot be 0, because if you raise 0 to any power, you're going to get 0, right? You're going to end up with a constant function. We don't want that. And also cannot be 1. Cannot be 1, because if the base is 1, 1 raised to anything is 1. We end up again with a constant function. We don't want that, right? So positive, but not equal to 0, not equal to 1. And x, exponent, that could be any real number, positive or negative, right? But the base always positive, not 0, no 1. Okay, examples of these exponential functions are f of x equal to the x, right? Just like the one that we saw here, right? This one, 2 to the t. This is one exponential function with base 2. However, the base, it doesn't have to be bigger than 1. Could be a number like 1/2. That's also acceptable. G of x equal 1/2 raised to x, which is the same as 0.5 raised to x. Is also another example of an exponential function, right? H of x 0.7 raised to x is another example of an exponential function, right? As long as this base is positive, not 0, not 1, then you got yourself an exponential function. Now, the first thing I want you to learn, guys, very well is this: evaluating exponential functions, okay? We're gonna do some computations that can be done in most of the cases only with a calculator. So I want you to learn how to do this accurately, right? Following instructions. As an example here, evaluate this exponential function f of x equal 2 to the x for x equal negative 3.1. Instructions to do rounding. Round your result to 3 decimal places. Okay, how we do that? Well, we're gonna take our calculator, and simply we do this, right? They want us to evaluate our function, which is this, at negative 3.1. So we take our function 2 raised to something, that's something they want it to be 3.1, right? And we compute this in the calculator. Now, how you do this in the calculator? How do you get the approximate value of this in the calculator, rounding to 3 decimal places? Well, you're gonna, in general, you're gonna hit 2. Then there's gonna be a key that's gonna show this v backwards, or in some calculators you have this x to the y, right? Hit that, then minus 3.1, and then enter or equal. I'm gonna do it here using my our Desmos Scientific calculator. So 2 raise here, you go to this guy, a to b, right? Allows you to type the exponent minus 3.1, And then I get the result. You see here, guys, the result. Now they want me to round it to 3 decimal places. So I go up to 3 decimal places. I notice that this is the number 6. So this has to end up being 0.117, right? 0.117, rounded to 3 decimal places. Okay, so 0.117. Excellent. Done. Example 2, and then I will give you something to work on your own. Example 2 says evaluate this other exponential function for x equal 1.5, round your result to 3 decimal places. So one more time, we need to evaluate our function at this value 1.5, right? Which is this. Our function is this exponential function. So we just put in the top 1.5, right? 1.5 instead of x. And then you do this in your calculator. So what is this equal to? Approximately equal to, right? Because they say rounded to 3 decimal places. Well, this will be 0.6 now. I'm using our Desmos scientific calculator raised to 1.5. And I get 0.4647. Because of this 7, this becomes 5. So 0.465, right? 0.465. That's it. All right, guys. So computation, right? We're going to need this for a lot of applications. So let's make sure that you guys are okay with this. So can you try number 1? This one. Use your calculator or our Desmos calculator and get number 1 done. This is computation, all right? Just get this done and let us know what you got for the answer. Hint, if you are using a scientific calculator, use this symbol, B backwards, or in some other calculators, they use this. Sometimes you have to hit shift or second to activate this key, right? In our calculator, A to B, I think it's this, right? And then after that, 3.5, and then you hit equal. That should give you the answer, right? Yeah, very good. Excellent, excellent. I see some activity in the chat. Anna, yeah, very good. Excellent, Anna. Excellent. You got it. You got it, right? Yeah, very good. Very good. When you do this, you get this. I will show you. 5 raised to, I'm using this, 3.5, simply 279.51. Professor, how big the number became? Yeah, guys, I explained to you, right, that exponential functions, they grow very rapidly. So not a surprise that the output values will be huge. All right, so this one rounded, right? Give me this 279.508 rounded to 3 decimal places. Excellent. Try this, guys, with a negative exponent. Do this now. 3 raised to, right? Here is negative 3.6 equal. Yeah, or x to y or a to b, right? Either way, it's fine. It depends on the calculator, but get it done. Practice, guys, because you're gonna need these computations for the applications. Anna, you made my day. Excellent, right? Very good, very good. Yeah, when you do this, again, we can do it as a way to practice. 3 raised to negative 3.6 gives us a very small number, 0.0191, right? Rounded to 3 decimal places, 0.019, right? Very good, guys. So this is just equal to 0.019. Excellent. This guy, right? Yeah, a small number because the exponent was negative, right? We will talk about that next. when we graph this exponential function. So now let's talk about the graphing, right, of these exponential functions. Go back to the lecture. And turns out when you graph these exponential functions, they're going to be just two scenarios, two cases, right, that you have to remember. The first case is this. Graph of exponential functions. The first case is when the base is greater than 1. Base 2, base 3, base 2.5, base 3.8. Any base bigger than 1, turns out, can be graphed in the following way. If you construct a little table for this function, I have chosen 0 at the center, 1 and 2 to the right, -1, -2 to the right. Notice 2 to the 0 is just 1, right? 1. 2 to the 1, 2 to the first power is 2. 2 to the second power, 4. 2 to -1, I show you how to do it in the calculator, is just 1/2, right? 0.5. You can check it in your calculator, right? 2 raised to -2 is 1/2 to the second, remember? 1/4, a quarter, right? 0.25. All right, so this is what we get, right? Let's just put this guy up here. Okay, great. Now, if you pair them up, input values with output values, you're gonna get the following. For zero here, this guy, right, 1. For 1, 2. For 2, 4. For -1, 0.5, half, right? For -2, 0.25, a quarter, right? Quarter. Now, when you join those dots with a smooth curve, you connect those dots with the smooth curve, better said, you're gonna get something like this, right? Smoothly. And this should be considered to be the graph of an exponential function whenever the base is bigger than 1, okay? Increasing from left to right. Let's write it out. Increasing curve from left to right. Increasing curve. From left to right, right? That's always the agreement for graphing. All right. Then this point is important where the exponential function meets the y-axis. It's called the y-intercept, right? The y-intercept. This point is going to be always 0,1 for the basic form, right? For the basic form of the exponential function, y-intercept. Y-intercept. And also you see here a line on the bottom, right? The x-axis, it's in blue. This is going to be an asymptote, a horizontal asymptote for this exponential function. Why do you say that, Professor? Well, because notice that the curve gets closer and closer to this line, never touching it, right? Never touching it for big values of x on the left. So it's a horizontal asymptote. Horizontal asymptote, let's write it down, right? Important feature, horizontal asymptote. And this horizontal asymptote has an equation, y equals 0 is the equation, right? The horizontal. So y-intercept here, horizontal asymptote, increasing from left to right. Great. This is the first scenario, right? Second scenario, what if the base is positive but less than 1? Some number between 0 and 1, some number between 0 and 1. Let's say, for example, 1/2, 1/3, 2/3, right? Could be. So let's see what happens. If we graph again by pairing up input values with output values, if I let my input values be 0 at the center, 1 and 2 to the right, -1 and -2 to the left, and I do what I did before, let's see what happens. Look, 1/2 raised to 0, 1/2 raised to 0 is just 1, right? Remember, any number raised to 0 except for 0 itself is just 1. Now, 1/2 raised to 1, what's that? Well, It's 1/2, but 1/2, 0.5, right? 1/2 raised to 2. 1 raised to the second power 1, 2 raised to the second power 4, a quarter again, 0.25. 1/2 raised to -1. Remember, when the exponent is negative, you flip the base, you get 2 raised to 1. This should be 2. And you can confirm all these computations the way I show you, right, in the calculator. 1/2 raised to -2, flip the base because of the negative sign, 2 raised to the second power, 4, right? 4. Great. Input, output. If you pair them up, look, 0 goes with 1, 0 with 1, 1 pair up with 0.5 here in the middle. 2 goes with 0.25 here, a quarter. -1 goes with 2. -2 goes with 4. Now, if you connect the dots, with a smooth curve again, you're gonna get something like this, right? Notice the curve now is decreasing from left to right, right? If you walk along the curve, you're going down now, right? Before we were going up, remember? Going up here from left to right, but this one going down from left to right. So it's a decreasing curve, from left to right, of course, right? From left to right. Great. Y-intercept, again, surprisingly the same, right? 0,1 Y-intercept. And surprisingly, also look at this line, this blue line. Isn't it true that the curve is getting closer and closer to this line, never touching it, right? So then we got ourselves a horizontal asymptote. And this has an equation. Y = 0 is the equation of the horizontal asymptote, right? Excellent. Okay, guys, now that we know that the graphs of exponential functions just come in two forms, either increasing when the base is bigger than 1, right? Or decreasing this way when the base is between 0 and 1. Let's do some graphing, right? Using also transformations. Transformations of graphs of exponential functions. Examples. Suppose they ask you to graph this function, g of x equal 4 to the x minus 2. 4 to the x minus 2. Well, you start sort of by remembering or identifying what looks familiar to you, right? This looks familiar to us, right? G of x equal 4 to the x, right? This is something that we just did. That the shape for the graph of this function is just this, right? Increasing, meeting the y-axis at 0,1. How do you know that, Professor? Well, because notice that 4, the base, right? 4 is bigger than 1. So this is the shape, right? Very good. An asymptote here at y = 0. Now, advice, guys, when you do these transformations, move the important features of the graph. What are the important features? The y-intercept and the horizontal asymptote. This is saying subtract 2 from any output value, right? Shift the graph down to units, right? We learned that when we did transformation, down to units, 2 units down. So what I want to do is this y-intercept has to appear here 2 units down. So look, 1, 2. So it will appear here, right? At this new place, right? It was here above, 1 unit above the x-axis, now ended up 1 unit below the x-axis, right? Similarly, the horizontal asymptote should go 2 units down. It's a level 0 here. So it should go 1, 2, 1, 2, right? 2, so will appear here. And right there, draw again your increasing graph, right? So this stays the same. Okay, so this will be g of x equal 4 to the x minus 2. I see someone writing something in the chat. Yeah, the xy point, Gabriela. Yeah, no, Gabriela, we started by saying, right, that we are going to graph this guy, just this guy first, right? G of x equal 4 to the x. How do I know that this is this curve? Because we explained that whenever the base is greater than 1, the graph will resemble an increasing curve like this. It will be steeper, of course, right? Yeah, probably that's why you probably mean. This will be steeper than g of x equal 2 to the x, perhaps, but this will be the shape, right? The main shape. You follow that, Gabriela, now? This was gotten from this because the base was greater than 1, right? We wrote it here, greater than 1, 4 greater than 1, right? Yeah. And then from there, we just put it down 2 units down. The x equal to this guy. Yeah, this we explained when we set x equal to 0, 4 to the 0 is going to be 1, right? So for x equals 0, the other point should be 1. It's a property, 0, 1, because 4 raised to 0, 1, right? We said that for any exponential function in basic form, this will be always the y-intercept. Now you follow, Gabriela? 4 raised to 0, 1. This was the x value. This was the y value, right? Right? Yeah. Oh, it will meet the graph. Great. Excellent. Now it's clear. Yeah. Whatever is not clear, guys, let me know. Let's clarify, right? Yeah. Questions are always welcome. Yeah. Write it in the chat. I will read it. Or you can say it verbally. Okay, guys. So this was the final graph, right? You see it? Yeah. So use the y-intercept, use the horizontal asymptote for transformations. Another example here. Graph f of x equal minus 5 raised to x plus 1. Start with something that you know, right? Let's start, say, this one I know, 5 to the x, right? Because we said that as long as the base is greater than 1, we know that it's going to look like this, right? An increasing curve. So start there, right? Start with something that you know. So we're going to start saying, okay, I know the graph of f of x equal 5 to the x, right? It's this. It's steep. This, right? The bigger the base, the steeper, right? Great. Now, this guy I know is 0, 1 because 5 to the 0, 1, right? We said it's a property of exponential functions. They, in basic form, they meet the y-axis at this point, 0, 1, right? And then it will show a horizontal asymptote at y equals 0, which is this. Now, there is a minus sign here, right? Minus sign here. So we're going to take care of that. This minus reflects this graph, right? Reflects this graph about the x-axis, right? So since the reflection is about the x-axis, the horizontal asymptote will stay at the same place, right? Yep. But this point will be reflected down here, right? Now it will appear here. 0, and the whole graph will be the mirror image of this guy down here, right? So we're talking about this guy now. Right? This will be f of x equal minus 5 raised to x, right? We just reflected. Now we're going to deal with this plus 1, right? This plus 1. This plus 1 now. Plus 1 says shift this up, right? 1 unit. Shift this up. When you do the shifting, when you shift up this y-intercept, shift up the horizontal asymptote. If you shift 1 unit up the y-intercept, look, it's going to end up here, right? At the origin here, right? You see, guys? And when you shift this up 1 unit, will appear 1 unit above the x-axis, right? So here. There, just draw this, right? That will be it. That will be it. So asymptotic here, like this. That's it. This will be your graph, right? Yeah, what I did here, I just shift it up 1 unit, right? It up 1 unit. Yep, that's what I did to go from here to here. And that's the final graph. This should be the graph of f of x. F of x equal minus 5 raised to x plus 1, right? Plus 1. That's it. Okay. Okay, guys. Now let me ask you to do some work, right? Take this as a reference, what I just did. It's not really that difficult, so try it out. There's a couple of examples there. So let's try the first one, number 3. Can you try this? Number 3. I'm gonna let you see the choices there. Yeah, there are just 2 choices. It's basic, but we start with something basic. Do this. Can you graph this function f of x equal 3 to the x plus 2? And choose either A or B. Which one? Yeah, the hint is start with this graph, right? Start with something that you know, this graph, right? And then do the shift, right? Shift. Yeah, and if you figure this out, just write it on the chat or let us know verbally. It's okay too. Yeah, probably. I see. Jay. Jamie, very good. Excellent, Jamie. So very good. You got it. Yeah, you start with something that you know, right? We know the graph of this guy, right? It's just this. Goes to this point, right? Asymptotically here and grows like this. This is f of x equal 3 to the x. But they want this plus 2, plus 2. Plus 2 means you shift this up, right? 2 units up. So means you are going to shift the y-intercept 2 units up, 1, 2. The new y-intercept will appear here. But also you have to shift up this line, the horizontal asymptote, right? It's a level 0. So if you shift this up, 1, 2, the new horizontal asymptote will appear here, right? And as a result of that, the new graph should be, will look something like this, right? Follow, guys? And it's clearly this. Follow? Great. Yeah, this graphing is not really difficult. Can you try this so we can move on? This number 4. Again, two choices there. Try this. Maybe we keep a little bit bigger. Yeah. You see it? Graph g of x equal equal 4 raised to minus x. And the hint is when, remember, the negative sign is applied to the inside of the function to the input value, you have to do a reflection about the y-axis, right? So do a reflection about the y-axis. It's a tricky question. Start as usual with this, right? With something that we know. This is the graph of f of x equal 4 raised to x. And for this minus there, you have to reflect it about the y-axis, right? About the y-axis. Tricky question. Yeah, if you figure it out, let us know. Yeah, the hint is right. This negative sign tells you reflect about the y-axis. Yeah, let's do it together, okay? Look, the negative sign on top of this means reflected about the y-axis. So this is the y-axis. We kind of place a mirror here and look at the reflection, right? The reflection. This point reflected about the y-axis stays at the same place. The horizontal asymptote stays at the same place. So this just would be this. Right? Yeah, very good. This would be f of x equal 4 raised to minus x. So more or less this, right? Yeah. You're gonna see the main shape. Follow, guys? All right. So let's continue. Yeah, and you may say, Professor, but this seems like it's touching it. Yeah, it's just you have to assume that this is not touching it, right? It's just that the quality of the printing doesn't show that this is an asymptote, right? But this is the one. Look at the main shape always, right? Main shape. All right, guys. So let's move on. Let's talk about a very interesting property about exponential functions. It is this. Exponential functions, they come into shapes, this shape and this shape, but no matter in what shape they appear, what is important is that they will always pass the horizontal line test, and therefore they are one-to-one functions. Exponential functions are one-to-one because they pass the horizontal line test. Will you show that, Professor? Sure. Look, this is one scenario, right? One way the graph of an exponential function could appear. You apply the horizontal line test, look, one point of intersection always, right? So this is one-to-one. Now, if your exponential function comes in this form, it's still one-to-one because no matter what horizontal line you draw, you will meet your graph only once, right? Once. All right, so it's a one-to-one function, exponential function. So now this can be used to solve very basic exponential equations. I will show you how. Example 1, suppose they ask you to solve 9 equal 3 raised to 2x minus 4. Solution, since we know that exponential functions are one-to-one, then to equal bases, it should correspond equal exponents, right? Equal exponent, because to the same input, it should correspond the same outputs. So the strategy is this, write both sides of the equation, as powers of one number. Look, this is 3, this is 9. We know that 9 is 3 squared, right? So let's write everything as powers of 3. If you run the powers of 3, 3 to the 0 is 1, 3 to the first power is 3, 3 to the second power is 9. Aha, this is here, right? So it is possible to write this 9 as 3 squared. The other side of the equation is written already as a power of 3, right? So leave it alone. So now when you look at this equation, notice the bases are the same. So the exponents should be the same, right? Because the functions, exponential functions are one-to-one. So somehow you forget about the bases, just set the exponents equal to each other. This way, right? And believe it or not, guys, this will allow you to solve this equation. 2x equal 6, and dividing both sides of this equation by 2, we get that x finally equal 3, right? 3. And that's it. We are done, right? We use the one-to-one property of the exponential function. We were able to solve this basic exponential equation. All right. Another example here. Let's say they ask you to solve this 1/2 raised to x equal to 8. The hint kind of is look at the smaller number, 2 and 8. The smaller number is 2, right? Run the powers of 2. Run the powers of 2. 2 to the first power 2, 2 to the 0, 1, 2 to the third power, 2 to the second power 2. Yeah, let's do it in order better. And eventually, when you get to the power of 3, you will get that this is just 8, right? Which is here. So let's use this and let's rewrite this 1/2 raised to x raised to 2 to the third. But now notice 1/2 is this 2 raised to minus 1, right? Remember this minus 1 tells you flip the base, raised to 1. 2 raised to minus 1 is 1/2, right? So this kind of goes up here as 2 to the minus 1, if you prefer. And what is important is this, minus 1 times x minus x equal to the third. This is what is important there, because we have finally the two sides of the equation expressed as powers of 2. Once you get there, you say, okay, remember, see, to equal bases, it corresponds equal exponents, right? It's kind of eliminating or forgetting about the bases, just setting the exponents equal to each other. That gives you a simple equation that you can solve and find your value of x. X equal 3 is the answer to this basic exponential equation, right? Later we will see more complicated ones, but I will give you other techniques, right? But in these cases, it is enough to express both sides of the equation using the same base and use the fact that exponential functions are one-to-one. I'm going to give you example, basic example for you to solve here. Why don't you try number 9 on the worksheet? Let's see, number 9 here. Can you try this? Let me make it very big. Everybody sees it? Yeah, this one. Do this. 2 raised to 3x minus 7 equal 4. Solve, right? Solve. Hint, comparing 2 and 4, 2 is the smallest, right? Use the powers of 2. Hint, use powers of 2. Use powers of 2. Try to do that, guys. It's not that difficult. Hint, use powers of 2. I see. For number 9, Gabriela, excellent, Gabriela. Yeah, you made my day. Yeah, excellent. It means that you guys have understood the technique. It's a very nice technique. Yeah, very good. Notice I have 2 raised to 3x minus 7 on the left. And if I run the powers of 2, 2 to the 0, 1, 2 to the first power 2, 2 to the third power 8. Here. Sorry, 2 to the second power, right? I skip 1 power. 2 to the second power is 4. Yeah, this is what we need. This is what I can use here, right? 2 to the second power is 4. Now, to equal bases, it corresponds equal exponents, right? Because exponential functions are one-to-one. So we forget about the bases, we set equal to each other exponents. From there, not hard to see, guys, that 3x equal 9, right? And divided by 3 both sides, x equal 3. Excellent. This guy, right? Excellent. That's for 9. What about number 10? It's a little bit tricky, but I think you will be able to handle it. 5 raised to minus x equal 1 over 25. Hint, use powers of, look, between 5 and 25, the smallest is 5. So use powers of 5, right? 5 to the 0, 1, 5 to the first power, 5. Go ahead, guys, and complete it. 5 to the second power, 25. Yeah, try to that. And those from these algebraic tricks, you should be able to figure this out. Yeah, the next hint probably should be that 25 from here, 5 is square, right? And try to write this 25 above here, above here. Remember, it's a technique. You make the exponent negative, right? Negative, and then you can put it up here. It's 5 raised to negative 2. And then noticing that the bases are the same, we can set the exponents to be the same, right? Aha, I see some activity in the chat room, which is good. Gabriela, excellent. Excellent, you made my day. Very good, very good. Excellent, excellent, right? Yeah. It's not that difficult because if you write here 5 raised to minus x, and here 1 over 5 squared, I have written 25 as 5 squared following these powers of 5, right? This is 5 raised to minus 2, right? When you put this up here, okay? Now, equal bases, to equal bases corresponds to equal exponents. So we forget about the bases. We set the exponents to be equal to each other, right? Like this. And then dividing both sides of this equation by this number, invisible one here, minus 1. Minus 1 into minus x is just x. Minus 1 into negative 2, 2. So we're talking about this guy, right? Excellent, excellent. Very good, guys. Very good. Excellent. Well, they call it natural exponential function because the base is special, is the number E, Euler's number. And when you use these natural exponential functions, you can model a lot of things that occur or happen in nature. The natural base E, Euler's number, in many applications, is the most convenient choice for a base. Okay, so is the most convenient choice for a base. Yeah, that is already written down here, so it's okay. Yeah, very good. Now, this number E is a special number just like pi. Its approximated value is 2.718288182 and so on. For us, we're going to take just three decimals, so E could be equal to 2.718. In any case, all calculators have this Euler number embedded in the keyboard, right? It's one of the buttons is E. So shouldn't be a problem, but just for you to know. Okay. F of x equal to x is called the natural exponential function because the base is E, right? Now notice, first thing, this E as a real number is 2.718 approximately, right? But that is greater than 1, right? Greater than 1. So when we graph this function based on the two scenarios, let me ask you this question. Do you think we will get a graph that is increasing or decreasing from left to right based on this? Anybody? Increasing or decreasing when we graph it? Okay. All right. While you think about it, let me do some computations here. Let's use this table. 0 at the center, 1, 2 on the right, -1, -2 on the left. E to the 0 is 1. E raised to 1. Remember, since E is 2.718, right? E to the second power, you can do it in your calculator. E, you raise this number to the second power, or you just hit where you see E on the keyboard to the second power, should be 7.389. E raised to -1, you're going to end up with this number, 0.367. And E raised to -2, 0.135. Sometimes you say, Professor, how do you do this calculation? Let's do it together so you can check. How I got this guy? E is here when you click in functions, e to the x, look for that, e to the x. E raised to 1 to raised to -1 is this guy, 0.3678, right? It's here. I just took 3 decimal places without even rounding. Yeah, this one, e raised to -2, approximately 0.135, right? It's there. Very good. Excellent. Someone, yeah, Gabriela. Yeah, Gabriela figured it out, right? Gabriela is saying that when we graph this, we should expect something that is increasing from left to right, right? Because we said that that's the scenario that corresponds to a base greater than 1, right? Excellent, Gabriela. Yeah, right? So if you pair up these points, for sure, guys, you are going to get something like this. You can do it at home, right? This, right? A curve that is increasing from left to right. It's an increasing function, but it's a special function, right? Not so steep, not somehow somewhere in the middle between the ones that are really steep, the ones that are really not, right? That makes it special, I think. It's related to the average values that appear in nature when you measure quantity. You will study this when you take statistics, for example, right? There is this so-called normal distribution. And this has to do with the number E, the Euler numbers, right? Euler's number. All right, but now we are going to focus our attention to the features of the graph first, right? As usual, this will meet, based on this result, this graph will meet still the y-axis at 0,1. And still you will see here on the bottom a horizontal asymptote. Horizontal asymptote. Whose equation is just y equals 0, right? This guy. All right. But now, we should really pay attention to one application of this. But before we go over application, the financial application, let's just go over general application. General application, Professor, what do you mean? Well, for example, in science, I explained to you, right? These functions appears a lot. I will show you how, guys. Here. There are 2 examples here. I'm going to go over one of them. The computational ones, I leave it for you to do it at home with a calculator, right? Easy. But this ones, I want to do number 7, and I will let you do number 8, okay? So let me explain. For example, here in number 7, it says the growth in the mouse population at a certain county dam can be modeled by the exponential function a of t equal 395 e raised to 0.013 t, right? Where t is the number of months, time, right? Since the population was first recorded. Estimate the population after 28 months. Yeah, what is remarkable, guys, is, as I said, right? If you choose the base to be e, turns out you can model the growth of population, for example, the population, the growth of this mouse population, right? Now, this is the basic form of the exponential function, right? There is a constant here. A constant is not one. We in the basic form is one, right? But it's a different number. Whenever that happens, this guy is the initial population. Initial population. Okay, corresponds to time 0. Okay, time 0, the 1 initial population, right? Yeah, great. So now they just want you to figure out what should be in average the population, an estimation, right? Estimate the population after 28 months. So let's see. So all you gotta do is, since we already have the function, we just let t be equal to t be equal to 28, right? Because t is measured in months. So let t be equal to 28. At t equal 28, look, this becomes a at 28, population after 28 months, 395 times e raised to 0.013 times, and here instead of t, you substitute 28. Compute this, guys, compute this, and approximately get population of mice. So we're going to do it together. Look, you take the scientific calculator or our Desmos scientific calculator if you prefer, and you type 395 times e. Where is e, professor? Function, and then e raised to something, e raised to. I have two numbers here multiplying each other, right? I want to keep them together. So just to play safe, I'm going to type within parentheses this 0.013 times 28, okay? Just to play safe again. Better safe than sorry, right? So look, all together, this is the exponent. So as a result, I get 568.43. I'm dealing with population of mice, right? So I have to round it to a whole number, right? For this to make sense. So I can round it to 568, right? 568 here. 568 mice after 28 months, right? Months. Very good, guys. So as you can see, it's a nice application, right, of the natural exponential function. Can you try now this one, number 8? I will leave this as a background for you to have, okay? Number 8, try to do number 8. Do this one. It says the function d of h equal a times e raised to minus 0.4 h can be used to determine the milligrams d of a certain drug in the patient's bloodstream 8 hours after the drug has been given. How many milligrams to 2 decimals will be present after 7 hours, right? Yeah, very good, guys. So try this. This is the equation or the function, and it's given, so just use this. Hint, let h be 7 hours, right? And then do the substitution as I did before there. Hint, let h be 7 hours, right? And compute this, d of 7, using your calculator. Go ahead, guys, go ahead, try it out. Notice there is a negative exponent. Be careful with the sign there. Aha. Some activity on the chat room. Let's check. Jay. Excellent, excellent. Very good, guys. Very good, great, excellent. You got it. Yeah, so if we substitute h for 7, right? So we're gonna get this. A times e raised to negative 0.4 multiplied by 7, right? By 7. But what is this approximately? Well, let's check, right? Let's check. Let's erase this part. Let's check that up. Yeah, let's do it together. Great. 8, then e. For e, you go to functions, then e to the x, right? E raised to what? To play safe again, guys, very important, parentheses, minus 0.4, right? Times, parentheses again, 7, right? Close parentheses again. Aha, look, the exponent all together, there's a multiplication, right? I get 0.486, right? Rounded to 2 decimal places as requested here, right? It will be 0.49, right? 0.49. So this is approximately equal to 0.49. And in the end, you may attach the units, right? Milligrams, right? Milligrams. That is what is left, right? Of the drug that was given to this patient, right? Yeah, it's, as you can see, right? Again, the natural exponential function appears as a good application in science, right? This health science. Very good, guys. So we're talking about this. Great, excellent. Now, let's see the application of this natural exponential function and exponential functions in general to calculate compound interest. Okay, there are two formulas that we're going to go through. So let me explain that to you. Let's go back to a lecture. Okay, so financial applications of exponential function. Compound interest can be calculated using a formula that is given by exponential function. Remember at the very beginning, I gave you these examples, right? Linear growth, exponential growth. This linear growth serves to compute simple interest, right? The one that you get added to your account every month, right? The same. But there is another type of interest called compound interest, which is interest that you gain, but what you have gained already is also considered for the next computation, okay? So it's sort of accumulated growth, right? And then therefore you get more money out of your investment, right? It's heavily used in investment. So we're gonna use these exponential functions to compute them. So how does it work? Well, the first scenario, there are two scenarios, is when you do the compounding over a fixed, or better said, a fixed number of times over a year, n times a year. If you compound the interest n times a year, then turns out this formula, a of t equal p times 1 plus r over n raised to n times t, serves to compute the accumulated value of your investment, right? A of t, amount after t years, p, principal is what you invest, right? R, interest rate per year. This has to be written in decimal form. Written in decimal form always. Let's explain this with examples. And number of times interest is compounded per year, okay? And T number of years for the investment, right? So let's see an example. But before we go over the example, let me show you how you have to get the value of this N. If they say that the interest is compounded annually, then N should be considered to be equal to 1, right? Because it's once a year. If they say that the interest is compounded semi-annually means that you do it twice a year, so N2. If they say that the interest is compounded quarterly means 4 times a year, okay, 4 times a year. If they say interest is compounded monthly means 12 times a year, right? Because 12 months make up for a year. Daily, we have to figure out how many days are in a year, but some years come with less days, leap years, right? It's not an exact amount, but mathematicians said as an agreement, take 365 days for a year, okay? So if they say daily, interest is compounded daily, take N to be equal to 365. Write this table down somewhere if you need to remember how to figure out the value of N. Example 1. This is from our worksheet, okay? It's exercise 12 in our worksheet. I'm going to do it here, and then I will ask you to do something else. It says, find the accumulated value of an investment of $13,000 at 4% compounded semi-annually for 9 years. Okay, so let's do it together. It says semi-annually means that my N for the formula has to be equal to 2, right? Has to be equal to 2. So keep that in mind. So we're going to apply this formula, right? A equal P times 1 plus R divided by N, all raised to N multiplied by T, right? Now, it says that the principal should be this 13,000, right? It's what you invest, right? 1 plus R. R is 4%, but we said that R has to be written as a decimal, right? So do this, 1, 2, 0.04, right? As a decimal. This is what you write here, 0.04. Or divide the number 4 by 100 in your calculator, will give you this, right? 0.04. N, what is N? Since they say that the interest has been compounded semi-annually, N equal to 2, right? Equal to 2. From our table, right? You can see. Now, N again, 2 times T. T is the number of years, 9 years, right? 9 years of this. Okay, so we have everything. We just need to do the computation, right? Let's do the computation and let's figure it out. So what is this approximately equal to? They don't tell you to round it to any number of digits, but by default, it's understood that you should round it up to cents, right? Because that is the way you deal with money, right? Up to cents. So let's do this computation and round it to 2 decimal places. So we take our calculator, right? 13,000 times parentheses 1 plus 0.04 divided by 2, close parentheses, and then raised to, be backwards, right? I want these two together, 2 times 9. 2 times 9. Professor, 2 times 9 is just 18. Yeah, but in case the numbers are not friendly, this is the way you have to type it in general, right? Worst case scenario. Look, result 18,567. 18,567.20, right? Rounded to 2 decimal places, up to cents. Let's write it out here. So 18,000 567.20, right? Dollars. In the end, you can attach the dollar symbol. That's it, right? Look, your 13,000 over 9 years became 18,567.20, right? Yeah, very good, very good. Very good, guys. So as you can see, it's a very nice application, right, of these exponential functions. Okay, so now I want you to practice. Remember, practice makes the master, especially in mathematics. So let's go to the worksheet and let me ask you to do something on your own. Can you try this one? I think this is number 13. Can you try this? I will give you the formula, okay? A equal principal times 1 plus r over n raised to n times t, okay? Yeah, and any of you could tell me what is n here based on this? This is quarterly. N should be equal to what? Gabriela, excellent, excellent. Yeah, I see you guys are 2, 4, right? 4 quarterly. Before it was 2 because it was semi-annual, right? But this is quarterly, so N4. Very good, very good. So yeah, just put everything in. Don't forget that the percentage has to be written as a decimal, right? And that should be it. Yeah, figure out, do the computation. Use your scientific calculator. You should be fine. Aha, I see activity in the chat room, which is good. Let me check. Gabriela, excellent, excellent work. Very good, very good. Yeah, I think you guys have understood this. It's not that difficult, right? You just have to carefully identify the components of the variable and then do the computation. Great, excellent. So accumulated value will be equal to present value, which is 1,200, right? Times 1 plus the rate. The rate is 8%, but 8%, remember, is just 0.08, right? As a decimal. And divided by n is 4. All raised to n for multiplied by the number of years for the investment, 2 years. Very good. Now let's compute this. Great, 1,200 times 1 plus 0.08 over 4, close parenthesis there, raised to, and I'm gonna write within parentheses 4 times 2. 4 times 2. Professor, 4 times 2 is 8. I know, guys, but in case it's needed, right? This is the way you have to type it out. 1,405.99, right? Yeah, so 1,405, let's write it to 2 decimal places. Remember, that's the agreement, $1,405.99, right? It kind of makes sense because, look, your 1,200 became 1,400 over 2 years, right? Makes sense, so everything good. Yeah, so therefore, the answer should be this, right? There's something written on the chat. Yeah, Halon. Yeah, very good. You got it too. Halon Chen. Yeah, excellent, excellent. Good work, good work. Excellent, excellent. Yeah, very good, guys. Yeah, I see you figure this out. Yeah, let's do another one. And then I will explain to you how to do it what was the case for continuously compounded? Okay, so try to do this now. Can you try it? Find the accumulated value of an investment of $5,000 at 5% compounded monthly for 8 years. Yeah, and then I will give you the formula. A equal present value 1 plus R over N raised to N times T, right? N times T. And anyone could tell me, based on this, what should be the value of N? Since it says compounded monthly, what should be the value N? Anyway? Gabriela, excellent. 12, right? Because 12 months in a year. Excellent. Yeah, from the table, right? And 12, yeah. Just do this and compute your compounded compound interest. Yeah. So your accumulated value, right? Better said. Practice, guys. Use your calculator or use our Desmo scientific calculator. Same, right? Yeah. Let's see, number 16. Yeah, very good, very good. Halo, excellent, excellent, excellent. Very good, very good. Excellent, yeah, great. So accumulated value for our investment will be equal to present value, $5,000 times 1 plus rate. Rate is 5%, but we write it as a decimal, right? 0.05 over N 12, because we are doing this compounded monthly. Raised to N 12 times the number of years. Number of years, 8, right? So this is what we're gonna do. Yeah, okay, so let's do it carefully. So we have 5,000 here, times, parentheses, right, 1 plus 0.05 over 12, close parentheses, raised to, I'm gonna open parentheses and type 12 times 8. 12 times 8, Professor, that's 96. Yeah, I know. But this guy's to play safe, right? Better safe than sorry. All right, so 7,452. Makes sense, right? 5,000 became 7,452 over 8 years. Makes sense. So rounded to 2 decimal places by default, right? So this becomes 93 then. So we're talking about choice B. Excellent, excellent. 7,452.93. And therefore, this is this guy. Excellent. Okay, now let me show you the second scenario, okay? The second scenario deals with compounding continuously, but what is that? What is compounding continuously? Let me explain that to you now. Okay, so we explained this formula, right? When your interest is compounded over a finite number of times in a year, right? Yeah. But now think about this, guys. Suppose you invest some money, right? And you do it yearly. Your interest is compounded yearly. You're gonna get certain amount in return accumulated, right? If you do it monthly, if you interest is compounded monthly, you will get more, right? More, because the exponent will be increased, right? And turns out when you do the computation, you'll get more. If you do it daily, since n is 365, even more. But turns out if you keep increasing the number of times your interest is compounded in a year, from daily you can go to hourly, every minute, every second, right? Turns out this growth is bounded above by some real number, by some real numbers. Mathematicians have discovered that, right? It's not like it's gonna grow like crazy, right? It's bounded, this growth, okay? And moreover, mathematicians figure out that that bound is somehow related to the Euler's numbers having as a base in an exponential function. So this growth is just this. The principal multiplied by e raised to RT, okay? It acts like an upper bound as a limit of the growth here, right? So this P e raised to RT is the highest amount of money you can get as a return, right? And in theory, it corresponds to the case when you calculate your interest compounded every instant, right? Think of every second, perhaps that might help, right? But in theory, it's really every instant. So that is why mathematicians call it continuously compounded interest, okay? Continuously compounded, and take it as an infinity, right? Doesn't have a value. So continuously compounded interest. So the formula is different than this, right? Notice there is no n. Instead, P, principal, times E, Euler number as a base, raised to R multiplied by time, number of years, right? No n, right? So it's called continuously compounded interest, okay? It's a second scenario. And there are just two scenarios. All right, so example, suppose they say, find the accumulated value of an investment of $9,500 at 7.4% compounded continuously for 6 years. Aha, I see this word continuously, or this phrase, better said, right? Compounded continuously, especially this word, inside the body of the word problem. So immediately I know that I have to use this formula, right? The second formula. So A equal P times E raised to RT, no n, appears in this formula. Okay, so the accumulated value of your investment will be principal, 9,500 times E is Euler numbers, we have it. R is 7.4%, right? But anyone could tell me what I should write in the formula. What is this in decimal version? Hint. What are we going to write in the formula? We cannot write 7.4, right? We have to write this divided by 100. Aha. Yeah, Gabriela, excellent. 0.074, right? Yeah, be careful, guys, there. 0.074, right? Result of moving the decimal point to place to the left. Times multiply by the number of years. Number of years, 6. 6 years, right? That's 6 goes there. And that's it. Basically, this is what we have to compute, right? Let's see what we get. A equal the following: 9,500 times E. Professor, where is E? Here, functions, E to the X. E to the X. E to the 0.074 times 6, close parentheses. I get 14,809.84, right? Rounded to 2 decimal places, up to cents. Very good. Let's write it out. So I got 14,809.84, right? That makes sense, right? Look, from 9,500, I ended up with 14,800 over 6 years, right? My interest was compounded continuously, right? This is the best I could get, right? The best. Great. So this is how this works. Now, guys, for you to practice, let me go over the worksheet. I think there is a nice exercise there. So let's check it out. And then probably we will compare both. Okay, this one, 15. Professor, how do you know that 15 deals with what we just did? Look at this, guys. Compounded continuously. Remember, as soon as you see this word continuously or this phrase compounded continuously, the body of the problem means that you have to use the second formula, right? Which I'm going to write for you as a hint. A equal P E raised to R multiplied by T. Okay, use that formula and try to figure this out. And let us know the answer in case you find it. I try to remember all this for you, homeworks, problems. And for your exam also, exam number 2, definitely this should be there, this part. Remember, 9% must be written as a decimal. Okay, let's write out the computation, right? P should be 8,000. E is Euler number. R should be, what should be R? Anyone could tell us? It says 9%, but what should we write here as an R?
0.09.
Excellent. Hello. Yeah, excellent, Gabriela, too, right? 0.09. Be careful there, guys, because if not, it's not going to work. It's going to give you some other number. Excellent. And T is just 4, right? 4, yeah. Let's get this done. Yes, I'll try to do that. Okay, so let's do it together so we can then do both at the same time. So we start with 8,000, right? 8,000 here times E. Where is E? Function. Or if you have in the calculator, look for where it's written E on the button. E to what? I'm going to put between parentheses 0.09 times 4. I get 11,466.635. So I'm going to run it to 64, the cents, right? So as a result, I get 11,466.64, which is this guy, right? Yeah, very good. Yeah, try to remember this, guys, especially for the special assignment 2. I think in the special assignment 2, they're going to ask you to do this. Now, Sometimes you may have to compare these two types of interest, right? The one done continuously versus the one done over some finite number of times within a year, right? So what do you mean, Professor? Comparison. Look at 17, for example. Let me show you 17. In this question, it says, right? I'm gonna do for you this one, and probably I will let you do number 18, okay? It says, suppose that you have $4,000 to invest. Which investment yields to the greater return over 6 years? 7.5% compounded continuously or 7.6% compounded semi-annually? Right? This is the choice. Solution here. Compounded continuously. Let's analyze the first scenario, right? Compounded continuously, compounded continuously. I have to use this formula, right? A equal P times E raised to RT, right? Where the present value should be this 4,000, right? $4,000. E raised to R. R for the first case is going to be 0.075, right? And T, the number of years, they say consider 6 years, right? 6 years. So let's do this. If I do that, go to my calculator, 4,000 times E function, E raised to something here, 0.075 times 6, right? Within parentheses 6. Great, I got 6,273.25, right? 25, so let's write it down. 6,273.25, right? Yeah, this is the first choice of investment. For the second one is compounded semi-annually. So compounded semi-annually, right? Yeah, and try to remember this for your special assignment too. I think they will give you a problem where you have to compare options for investments. All right, compounded semi-annually. Well, this means that N is equal to 2, right? Twice a year. So my accumulated value will be P times 1 plus R over N raised to N times T. Accumulated value will be present value 4,000 times 1 plus R. R 7.6%, right? But remember, we move these two places to the left. Or with a calculator, we divide that number by 100. This is it. N is 2. So all raised to N 2 times the number of years. The number of years is 6, right? So let's see how much we would get. So again, you go to the scientific calculator or our Desmos scientific calculator. I strongly recommend you to use, guys. It's free. It will always be free, and it's very useful, right? Yeah. Raised to 2 times 6, which is just 12, right? Let's put it this way in general. All right. I got 6,257.89. Let's write it out. 6,257.89. So this is this. So which is the winner? Comparing these two amounts, clearly this guy winner, right? You see, guys? So this is better. So therefore, I have to go with choice C, right? Continuously turn out to be better than doing this semi-annually, even though they increase a little bit the rate, right? Yeah. So you will have to. Can you try number 18? I'm going to leave this as a reference. Yeah, it's a little bit tricky, but I think you can handle this. Two scenarios, right? Two types of investments, go through both and figure out what is the best. Yeah, maybe I should write the formula here for these scenarios. A equal P 1 plus R over N raised to N times T, right? Yeah. And there are two scenarios, do both. One is compounded quarterly, right? And the other monthly, compounded monthly first. And the other scenario is compounded quarterly. Yeah, do both. Yeah, and as an extra hint for N compounded monthly, remember N12, for compounded quarterly, N4, right? Because 12 months in a year, quarterly, 4 quarters in a year. Say. Okay, guys, let's do it together. Okay, it's a little bit long. Yeah, remember this will serve you for your special assignment too. The first option for investment is compounded interest compounded monthly, right? N equal 12. Let's see how much money we would get out of investing following this. Accumulated value is equal to present value, which is 3,000, right? Times 1 plus R. R is here 7.2. So what I have to write here is 0.072, right? Over N, N is 12, right? 12, and all that raised to N, 12 times the number of years for the investment, which is 5. This is one computation. So let's compute this together. I'm gonna use my Desmos scientific calculator. 3,000 here times 1 plus 0.072 over 12 raised to 12 times 5. Professor, 12 times 5 is just 60, right? You can write 60 there if you prefer, guys. Writing the whole thing. All right, I got 4,295.37, right? Rounded to 2 decimal places up to cents. So 4,000 295.37. Let's do now interest compounded quarterly. N equal 4, so accumulated value will be present value 3,000 times 1 plus the rate. The rate is now 7.3%, right? So I gotta write this as a decimal, 0.073 over n, but n is 4 now, raised to n 4 times the number of years. Number of years is 5. So let's compute this. In dollars, we're gonna get the following: 3,000 times 1 plus 0.073 over 4 raised to 4 times 5. Or you can just type 20 there, right? Yeah, up to you. I get 4,307.34 now. 4,307. 307.34, right? Now, guys, comparing the two accumulated values, right? Which choice do you think we should pick there? A, B, or C? Which one? In other words, right? Which is the winner investment? Which one returns more money after 5 years? Okay, guys, since we are running out of time, comparing the accumulated values, clearly the second investment is better, right? Slightly better. 4,307.34 compared to 4,295, right? So this one winner. So if you go through the choices, they're a little bit tricky. The last one is the one that says that, right? Look, this one, it says, very good, very good. Yeah, very good, Anna. Yeah, very good. Yeah, it's tricky because the wording, the order of the investment, but try to follow this when you do your special assignment. There are a couple of questions related to this part. So always go back here and check. Very good, very good. You got it.